Alright, so this is going to be Chapter 10, Gases, Their Properties and Behavior. The final chapter we're going to be covering in Chem 1211 this semester. So gases are one of the three main states of matter, along with solids and liquids. And solids and liquids, compared to each other, are pretty different in comparison with gases. Specifically, solids and liquids together are often referred to as condensed matter because the particles are packed together much more tightly in in solids and liquids than they are in gases. So gas molecules are spread very far apart compared to liquids or solids, and the molecules in a gas essentially are free to move around at random. And they basically all go along in straight line paths, bouncing off their containers, only occasionally running into each other. And if you have a container with gas molecules in it, it turns out that under most circumstances at least, the gas molecules make up only a tiny fraction of the total space. So gases are actually mostly made up of empty space. When gases collide with the inside walls of the container that they're in, this phenomenon is responsible for pressure, which is fundamentally a measure of force per unit of area. So if you take the amount of force applied and divide it by the area over which that force is applied, you get the pressure. And there are different units of pressure to measure this that we'll go over in this chapter. And the pressure of Earth's atmosphere that you feel at ground level, so 1 atmosphere of pressure, give or take, is actually due to the weight of the gas molecules directly above you. So if you take a 1 square meter section of area on the ground, which is about 3 feet by 3 feet, and you imagine basically a column going up from the ground in that area straight up into space, all the way to the top of the atmosphere, the mass of the gas contained in that area all the way up to space is about 10,000 kilograms, which works out to be about 10 tons. Considering that the distance from the ground to the top of space is something like 60 miles or about 100 kilometers, that's actually not all that heavy because gases are pretty dilute and they become more dilute the higher up in the atmosphere that you go. So this is what's responsible for the gas pressure that you feel at the surface of the Earth. Now, there are several ways to measure gas pressure. One of the most basic ones, and one of the earliest ones discovered, is a device called a barometer. So a barometer takes a dish filled with some sort of liquid. Mercury, the liquid metal, is most commonly used for this purpose for reasons that I'll discuss in a minute. But you have a liquid-filled dish, and you have a tube inserted into that dish that's closed off at one side, and there's completely empty space in that tube above the liquid. So there's just a vacuum up there. There's no gas to push down on the liquid. And since there's nothing pushing back on the liquid, the atmospheric pressure pressing down on the liquid in the dish will force some of the liquid up the glass tube. And as it turns out, the distance that the liquid travels up the tube is directly proportional to the atmospheric pressure. And so we can essentially label the barometer with a ruler to just be able to measure the distance that the liquid travels up the tube, and that will give us a measure of what the pressure is in the atmosphere wherever the barometer is. Now, the reason why mercury is used for this as opposed to something more common and much more safe, like, say, liquid water, is another factor that influences the distance that liquid will travel up that tube is the density of the liquid. Now, mercury is about 13.5 times the density of water, and that means that it will travel a distance that is about 13.5 times shorter than water would in the same sort of setup. So, as it turns out, with atmospheric pressure, mercury will travel about 760 millimeters up a tube in a barometer, which is somewhere between 2 to 3 feet. So that's a relatively manageable distance, something that you can actually measure relatively easily. If you were to do this with water, that distance would be about 13 and a half times larger, and it turns out that water will travel about 30 feet up a tube. So that's really sort of unmanageable with atmospheric pressure. So that's why we use mercury, even though it's more expensive and dangerous. There are different units for measuring pressure. Many of them are related to each other in exact ways that we'll cover in a little bit. The most sort of fundamental unit of pressure, but not one that gets used very often, is the Pascal, PA. This is derived from the SI base units directly, and the reason why we don't use it is that it's way too small for measuring stuff like atmospheric pressure conveniently. 1 Pascal is about 100,000 times smaller than the atmospheric pressure at the surface of the Earth on average. So we have other units for measuring pressure that are more convenient. The units torr and millimeters of mercury are exactly identical in the same way that, say, milliliters and cubic centimeters are exactly the same thing. The unit of the atmosphere is basically what the average pressure is at sea level on Earth's surface. It's about 100,000 pascals or so. Or in terms of millimeters of mercury or torr, it's about 760 millimeters of mercury. And the unit millimeter of mercury is literally referring to the distance that the pressure in question will push mercury up an evacuated tube in a barometer setup. And finally, we have units of bar. That one's not very common. It's very close, but not exactly the same as 1 atmosphere. So, like I said, some of these relationships are exact. 1 atmosphere is exactly the same thing as 760 millimeters of mercury, or 760 torr, since those units are interchangeable. And 1 bar is exactly 100,000 pascals. That's very close to an atmosphere, but an atmosphere, more precisely, is actually about 101.3 thousand pascals. So an atmosphere is very slightly larger than 1 bar by about 1.3%. Alright, so we have several laws in chemistry and physics that we can use to describe the physical properties of gases. And it turns out that there's 4 important parameters for describing how gases behave. And the 4 parameters are pressure, which we abbreviate P, temperature, which we abbreviate with a capital T, volume, which we can use V for, and N, the number of moles of gas particles or gas molecules in the sample. So all 4 of those things are largely what's responsible for the physical properties of a gas under any given set of circumstances. Let's look at some laws that will actually relate pairs of these variables to each other. So for all these laws, we're going to look at the relationship between 2 of the variables. So for instance, in Boyle's law, volume and pressure. And whenever we do this, we're going to consider all the other variables constant. So in the case of volume and pressure, if we want to measure how exactly those 2 things affect each other, we need to assume that both the temperature and the number of moles of gas particles will stay the same. So if you wanted to measure the relationship between volume and pressure, you could imagine putting a gas inside of a sealed container with a movable piston, where we can adjust the pressure on the piston and see how the volume changes. So as it turns out, volume and pressure are inversely related to each other. So if you have a system where you have a volume of gas that's initially 1 liter and it's under a pressure of 1 atmosphere, if you double the pressure, the volume gets cut in half. And I think that kind of makes sense if you think about it. The increased pressure is going to press down on the gas harder, and it's going to contract it. Likewise, if you were to, say, take the cylinder on the right and start at a volume of half a liter and reduce the pressure from 2 atmospheres to 1 atmosphere, so reduce the amount of pressure pushing down on the gas, it'll be able to expand some, and specifically it will double the volume when you cut the pressure in half. So there's an inverse relationship between those 2 things. If we look at plots of pressure versus volume, if we just plot them directly, what we get is a graph that kind of looks like a y equals 1 over x graph, if you've ever seen one of those. That's what the shape of the graph on the left there is. If we want to do this in a little bit easier way, we can actually plot volume versus inverse pressure. So take pressure values, do 1 divided by those pressure values on the x-axis, and then volume on the y-axis. And that'll give you a straight line, since we've inverted one of the variables. So that's Boyle's law. Another way of stating Boyle's law is that the pressure times the volume will give you a constant, because that's a relationship that is exhibited by variables with an inverse relationship. And finally, again, if we assume constant n and constant t, so no change in temperature or the number of gas particles, the initial pressure and volume of a gas system, if you multiply those two things together, will be equal to the final pressure and volume multiplied together. So that's the relationship between pressure and volume. Let's take a look at the relationship between volume now and temperature. And it turns out that, again, assuming the other variables are constant, in this case the number of moles and the pressure, the volume and temperature of a gas are directly proportional as opposed to inversely proportional. So if the temperature goes up, so does the volume. If the temperature goes down, the volume does as well. Now, it's worth pointing out that the direct relationship between volume and temperature, at least quantitatively, is actually related to not the Celsius temperature or the Fahrenheit temperature, but the Kelvin temperature of the gas. So if we're doubling a temperature and expecting the volume to double, we need to be talking about that in terms of the Kelvin temperature. So for instance, if we start there on the left with a container with half a liter of gas, and there's a pressure of 1 atmosphere, if we heat that from 200 Kelvin to 400 Kelvin without changing the outside pressure, it's still 1 atmosphere, we're going to double the volume as well as the temperature, so the volume is now 1 liter. Likewise, if you cut the temperature in half from 400 to 200 Kelvin, you would expect the volume to be cut in half. And so if you plot temperature versus volume, you get a straight line graph like these. In fact, this works for both Kelvin and degrees Celsius, but if you plot degrees Celsius versus volume, you have a slightly trickier situation to handle because the y-intercept is not 0. If we're dealing with Kelvin, then all we need to do is multiply. We don't need to try to worry about some offset due to the y-intercept. Because of the direct relationship between volume and temperature, assuming constant moles of gas and pressure, volume divided by temperature will remain constant as long as n and p do. So that means that if we have some initial volume and temperature, if we take the initial volume and divide by the initial temperature, that is going to be equal to the final volume divided by the final temperature. So if you know any 3 of those, you can solve for the 4th. Finally, let's look at one more relationship, this one between volume and the number of moles of gas particles. So this is also a direct relationship, assuming that the temperature and pressure stay constant. So if we go back to one of these containers with a movable piston in it, if we have conditions of what are called standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure, it turns out that most gases, if we have 1 mole of those under those conditions, will actually have a volume of about 22.4 liters. And if we were to take that 1 mole of gas and introduce another mole of gas to get 2 total moles of gas, if the pressure doesn't change and the temperature doesn't change, the volume will double. And at standard temperature and pressure, that would mean we'd go from 22.4 liters up to 44.8 liters. Likewise, if you remove, say, half of the gas in a cylinder, then the volume would be cut in half as well. And so just like volume and temperature, all the same sort of relationships apply. Volume divided by the number of moles of gas particles will stay constant as long as T and P do. And so the initial volume divided by the initial number of moles of gas will be equal to the final volume divided by the final number of moles of gas.